Welcome! In today's session, we will tackle LeetCode problem number 1144, decrease elements to make array zigzag. This problem challenges us to transform an array into a zigzag pattern, where elements alternate between being smaller or larger than their neighbors. Let's dive in and explore how we can solve this step by step. The problem asks us to transform a given integer array into a zigzag array with the fewest possible moves. A zigzag array follows a specific pattern. At odd indices, each element must be strictly greater than its neighbors, while at even indices, each element must be strictly less than its neighbors. For example, at index 1, the value should be greater than both the values at indices 0 and 2. Similarly, at index 2, the value should be less than both the values at indices 1 and 3. Our allowed operation is to decrement any element by 1, and each decrement counts as one move. The input is a list of integers, and the output is the minimum number of moves needed to achieve the zigzag pattern. Let's now explore some examples to clarify this further. In the first example, the input array is 1, 2, 3. To make it a zigzag array, we have two strategies to consider. First, we can focus on making the even indices smaller than their neighbors. For this, we decrement the value at index 1 by 1, turning 2 into 1, and then decrement the value at index 2 by 2, turning 3 into 1. This results in the array 1, 1, 1, with a total of 3 moves. Alternatively, we can make the odd indices larger than their neighbors. Here, we only need to decrement the value at index 1 by 1, resulting in the array 1, 1, 3, with a total of 1 move. The minimum of these two strategies is 2 moves, which is our result for this example. In the second example, the input array is 9, 6, 1, 6, 2. Again, we evaluate two strategies. For the even indices case, we make index 0 smaller by decrementing it by 3, turning 9 into 6. At index 2 and index 4, no changes are needed. The total for this strategy is 3 moves. For the odd indices case, we decrement index 1 by 1, turning 6 into 5, and similarly decrement index 3 by 1, turning 6 into 5. The total for this strategy is 2 moves. Between the two strategies, the minimum number of moves is 4, so that is our result for this example. Now, let's look at the third example, where the input array is 7, 4, 8, 9, 7, 7. For the even indices case, we start by decrementing index 0 by 3 to make it 4, then decrement index 2 by 1 to make it 6, and finally decrement index 4 by 2 to make it 5. This results in a total of 6 moves. For the odd indices case, we decrement index 1 by 0 as no change is needed, and decrement index 3 by 2 to make it 7. This results in a total of 2 moves. When comparing the two strategies for the third example, the minimum number of moves required is 6. Finally, let's consider some constraints and edge cases. The array can have a length between 1 and 1000, and each element can range between 1 and 1000. If the array has only one element, no moves are required since it already satisfies the zigzag condition. On the other hand, if all elements are equal, adjustments will be necessary to create the zigzag pattern. These considerations highlight the importance of evaluating both strategies to find the most efficient solution. To solve the problem of transforming an array into a zigzag pattern, we first need to understand what a zigzag pattern entails. In this case, at odd indices like 1, 3, and 5, the element must be strictly greater than its adjacent neighbors. On the other hand, at even indices like 0, 2, and 4, the element must be strictly less than its neighbors. The challenge lies in ensuring these conditions are met for all indices in the array. To tackle this, we can break the problem into two subproblems. The first is ensuring the zigzag condition holds for even indices, and the second is ensuring it holds for odd indices. With this in mind, we can explore different approaches to solve the problem efficiently. One approach we might consider is the brute force method. The intuition here is to try all possible combinations by iteratively making adjustments to the array. Specifically, for each index, we check if the current element satisfies the zigzag condition. If it doesn't, we decrement the value of the element to the minimum required to meet the condition. The process involves iterating through all indices, identifying violations, and adjusting elements accordingly. We then compute the total number of decrements needed. This is done separately for both zigzag patterns, one starting with even indices and the other with odd indices. However, while this approach is relatively simple to implement, it requires checking and adjusting elements repeatedly, leading to a time complexity of O(n squared). This makes it impractical for larger arrays, as the computational cost grows significantly. Instead of the brute force method, we can employ an optimized approach that significantly reduces the time complexity. The key insight here is that the zigzag pattern can only start in two ways, either with even indices or with odd indices. By simulating both patterns separately, we can calculate the minimum number of decrements required for each. The main observations are straightforward. To satisfy the zigzag condition at any index, the current element must be strictly less or greater than its neighbors. If this condition is violated, we calculate the minimum adjustment needed. By processing the array in a single pass for each pattern, we can determine the total cost efficiently. Specifically, we initialize two counters, one for the even zigzag pattern and one for the odd. For the even pattern, we iterate through all even indices, checking for violations and accumulating the necessary adjustments. We repeat the same process for odd indices, storing the results separately. Finally, the solution is the minimum of the two totals. The optimized approach offers substantial improvements in efficiency. With a time complexity of O(n), we only need to process the array twice, once for each pattern, making it well suited for large input sizes. Additionally, the space complexity is O(1), as no extra data structures are required. While this approach is slightly more complex to implement than brute force, the performance gains make it worth the effort. Ultimately, we selected the optimized approach as our strategy because it strikes the right balance between clarity and efficiency. The key breakthrough was recognizing that the problem could be divided into two independent zigzag patterns. By focusing on the cost of conversion for each pattern separately, we eliminated unnecessary computations. This led to a clean, efficient solution that handles the problem effectively, even for large arrays. In this problem, we are tasked with transforming an array so that it adheres to one of two possible zigzag patterns. The first pattern requires that elements at odd indices are strictly greater than their adjacent neighbors, while elements at even indices are strictly less than their neighbors. The second pattern flips this requirement: elements at even indices must be strictly greater than their neighbors, and elements at odd indices must be strictly less. Our goal is to find the minimum number of decrements needed to transform the array into one of these zigzag patterns. The challenge lies in calculating the cost of adjustments for both patterns and deciding which one results in the least modifications. To solve the problem, we start by initializing two variables, cost1 and cost2, to track the total cost of modifications for each pattern. Both are initially set to 0. We then iterate through the array, examining each index I. For pattern 1, if the index is even, we ensure the element is strictly less than its neighbors by calculating the decrements needed. If the index is odd, we ensure the element is strictly greater than its neighbors. Similarly, for pattern 2, we reverse these conditions. Even indices must now be greater than their neighbors, and odd indices must be smaller. For each index, we calculate the decrements required using the formula max, 0, nums, I, neighbor 1, where the neighbor is the adjacent value being compared. These decrements are added to cost1 for pattern 1 and cost2 for pattern 2. When handling edge cases, it's important to account for the first and last elements of the array, as they each have only one adjacent neighbor. For these indices, we compute the required decrements based solely on their single neighbor. Once we've processed all elements of the array, we return the smaller of cost1 and cost2 as our final result. This ensures that we've chosen the pattern with the minimum transformation cost. The two-pattern approach is necessary because there are two valid zigzag configurations, and testing both guarantees we find the optimal solution. By calculating decrements theoretically instead of modifying the array directly, we avoid unnecessary operations and improve efficiency. Special cases, like single-element arrays or arrays with all equal elements, are also addressed to handle all possible inputs robustly. The algorithm is space-efficient since it uses the input array directly without creating additional data structures. The only extra space required is for the two integer counters, cost1 and cost2, making the space complexity O(1). The time complexity is O(n), as we make a single pass through the array, performing constant time calculations for each element. This combination of minimal space usage and linear time complexity ensures the solution is both practical and scalable, even for large input arrays. Let's walk through an example with the input array nums equals 9, 6, 1, 6, 2. For pattern 1, where even indices are less and odd indices are greater, we calculate the cost for each index. At index 0, we decrement 9 to 5, costing 4. At index 1, no change is needed. At index 2, no change is needed. At index 3, we decrement 6 to 3, costing 3. At index 4, we decrement 2 to 0, costing 2. The total cost for pattern 1 is 9. For pattern 2, where even indices are greater and odd indices are less, we calculate again. At index 0, no change is needed. At index 1, we decrement 6 to 0, costing 6. At index 2, we decrement 1 to 0, costing 1. At index 3, no change is needed. At index 4, no change is needed. The total cost for pattern 2 is 7. The minimum of these two costs, 7, is the final result. This code solves LeetCode problem number 1144, decrease elements to make array zigzag. The goal is to modify the array such that it forms one of two zigzag patterns, either odd indices or peaks or even indices or peaks. First, the code defines a helper function cost_to_make_peak index. This function calculates the cost of reducing the value at a given index to ensure it's strictly less than both its neighbors. If the index is at the boundary, it assumes the out-of-bound neighbor is infinity to avoid unnecessary reductions. The code then initializes two variables, odd_indices_cost and even_indices_cost, which track the total cost of making the array conform to the two zigzag patterns. For each index in the array, it checks whether the index is odd or even. If the index is even, it adds the cost of making it a peak to even_indices_cost. Similarly, if the index is odd, it adds the cost to odd_indices_cost. Finally, the function returns the minimum of these two costs, as we only need to achieve one of the two patterns. This ensures the solution is optimal with a complexity of O(n), where n is the length of the input array. This is the Java implementation of LeetCode problem number 1144, decrease elements to make array zigzag. The implementation mirrors the logic of the provided Python solution. Key differences include explicit type declarations, the use of Java's math utility for calculations, and encapsulating the helper function within the main class. The algorithm computes the cost of converting the array into a zigzag pattern for both even and odd indices and returns the minimum cost. To solve this problem, we start with an example input of 1, 2, 3. First, we initialize two variables, odd_indices_cost and even_indices_cost, both set to 0. These will track the total cost required to make the array zigzag for odd and even indices, respectively. Next, we define a helper function called cost_to_make_peak index. This function calculates the cost of reducing the value at a specific index so that it becomes a peak, adhering to the zigzag condition. Now, let's process the first element at index 0, which is an even index. Here, nums 0 is 1, and since there's no left neighbor, we set left to infinity. The right neighbor is nums 1, which is 2. To ensure that nums 0 is smaller than both its neighbors, we calculate the cost as max 0 nums 0 min left right plus 1. Substituting the values, this becomes max 0 1 to 2 plus 1, which equals 0. So, we add 0 to even_indices_cost, keeping it at 0. Next, we process index 1, which is an odd index. Here, nums 1 is 2, with left being nums 0 equals 1 and right being nums 2 equals 3. To make nums 1 smaller than both neighbors, we calculate the cost as max 0 nums 1 min left right plus 1. This evaluates to max 0 2 to 1 plus 1, which equals 2. Adding this to odd_indices_cost brings it to 2. Continuing with the example, we now move to index 2, which is an even index. Here, nums 2 equals 3. The left neighbor is nums 1 equals 2, and since there's no right neighbor, we set right to infinity. To make nums 2 smaller than both neighbors, we calculate the cost as max 0 nums 2 min left right plus 1. Substituting the values, this becomes max 0 3 to 2 plus 1, which equals 2. Adding this cost to even underscore indices underscore cost brings it to 2. At this point, we have processed all indices for this example. The final step is to return the smaller of odd underscore indices underscore cost and even underscore indices underscore cost. Since both are equal to 2, the result for this example is 2. Now, let's look at a new example with the input 9, 6, 1, 6, 2. Once again, we initialize odd underscore indices underscore cost and even underscore indices underscore cost to 0. For the first element at index 0, which is an even index, nums 0 is 9. Without a left neighbor, left is set to infinity, and the right neighbor is nums 1 equals 6. The cost to reduce nums 0 to meet the zigzag condition is max 0 9 to 6 plus 1, which equals 4. Adding this to even underscore indices underscore cost updates it to 4. Next, we process index 1, which is an odd index. Here, nums 1 is 6, with left equals nums 0 equals 9 and right equals nums 2 equals 1. The cost to make nums 1 smaller than both neighbors is max 0 6 min 9 1 plus 1. This evaluates to max 0 6 to 1 plus 1, which equals 6. Adding this to odd underscore indices underscore cost brings it to 6. Now, for index 2, which is an even index, nums 2 equals 1. The left neighbor is nums 1 equals 6, and the right neighbor is nums 3 equals 6. To satisfy the zigzag condition, we calculate the cost as max 0 1 min 6 6 plus 1, which equals 0. Adding this to even underscore indices underscore cost keeps it at 4. Next, for index 3, which is an odd index, nums 3 is 6. The left neighbor is nums 2 equals 1, and the right neighbor is nums 4 equals 2. To make nums 3 smaller than both neighbors, the cost is max 0 6 min 1 2 plus 1. Substituting the values, this becomes max 0 6 to 1 plus 1, which equals 6. Adding this to odd underscore indices underscore cost updates it to 12. Finally, for index 4, which is an even index, nums 4 equals 2. Here, the left neighbor is nums 3 equals 6, and without a right neighbor, right is set to infinity. The cost to make nums 4 smaller than its neighbors is max 0 2 min 6 inf plus 1, which equals 0. Adding this to even underscore indices underscore cost leaves it at 4. The final step is to return the smaller of odd underscore indices underscore cost and even underscore indices underscore cost. Here, the result is min 12 4, which equals 4. For the final example, we use the input 1 1 1. As before, we initialize odd underscore indices underscore cost and even underscore indices underscore cost to 0. Starting with index 0, which is an even index, nums 0 equals 1. Without a left neighbor, left is set to infinity, and the right neighbor is nums 1 equals 1. The cost to make nums 0 smaller than its neighbors is max 0 1 min inf 1 plus 1, which equals 1. Adding this to even underscore indices underscore cost updates it to 1. Next, for index 1, which is an odd index, nums 1 equals 1. The left neighbor is nums 0 equals 1, and the right neighbor is nums 2 equals 1. The cost to make nums 1 smaller than its neighbors is max 0 1 min 1 1 plus 1, which equals 1. Adding this to odd underscore indices underscore cost updates it to 1. Finally, for index 2, which is an even index, nums 2 equals 1. The left neighbor is nums 1 equals 1, and without a right neighbor, right is set to infinity. The cost is max 0 1 min 1 inf plus 1, which equals 1. Adding this to even underscore indices underscore cost brings it to 2. The result for this example is the smaller of odd underscore indices underscore cost and even underscore indices underscore cost, which is min 1 2, and that equals 1. To analyze the time complexity of this solution, we start by considering the main loop that iterates through the nums array. This loop runs once for each element in the array, so its contribution to the time complexity is O, n, where n is the length of the input array. Within this loop, the function cost_to_make_peak is called for each element. Inside this function, operations like accessing array elements using indices, as well as using the min and max functions, are all O(1) operations, as they involve constant time comparisons or retrievals. Therefore, the cost_to_make_peak function contributes O(1) for every iteration of the loop. Since the function is called once for each element, the total contribution remains O(n). Finally, after the loop, there is a comparison between two integers to find the minimum cost, which is also an O(1) operation. Altogether, the time complexity of the solution is determined by the loop, making it O(n). Summarizing the total time complexity, the single loop over the array dominates the overall runtime, resulting in O(n). Now let's shift our focus to space complexity. The input array nums is stored in memory, which contributes O(n) space. Beyond this, the solution uses a few auxiliary variables like odd_indices_cost, even_indices_cost, and temporary variables such as left, right, and the result from cost_to_make_peak. All of these are integers and take up constant space, contributing O(1) in total. Importantly, no additional data structures like lists or recursive calls are used, meaning the algorithm doesn't require extra memory for intermediate computations. Therefore, while the input storage requires O(n) space, the algorithm itself uses only O(1) additional space, making it very efficient in terms of memory usage. Now, comparing this optimized approach with a naive or brute force solution highlights the efficiency of our method. A naive approach might involve generating all possible zigzag configurations by iterating over the array and decreasing values one by one to calculate the cost of each configuration. This would result in exploring all possible combinations, leading to exponential time complexity of O(2 to the power of n) in the worst case. Additionally, such a brute force method might require storing intermediate states, which would increase space complexity beyond O(1). In contrast, the optimized approach avoids generating all configurations and directly calculates the cost for odd and even indices in a single pass. This not only reduces the time complexity from O(2 to the power of n) to O(n), but also minimizes the space complexity, requiring only O(1) auxiliary space apart from the input storage. Finally, let's break down the best, average, and worst-case scenarios for this solution. Regardless of the input, the algorithm always iterates through the array once, making the time complexity O(n) in all cases. In the best case, where the array may already be close to a zigzag pattern, the algorithm still performs a single pass, resulting in O(n) complexity. Similarly, in the average case, where the input may have a typical distribution of values, the runtime remains O(n). Even in the worst case, such as an array with the maximum size of 10 to the power of 5 elements, the algorithm efficiently completes its single pass in O(n) time. From a mathematical standpoint, the loop runs n iterations, each taking constant time, which confirms the time complexity is O(n). The auxiliary space usage remains constant at O(1), while the input storage contributes O(n), making the overall space complexity O(n). This efficient design ensures that the algorithm performs optimally across all scenarios. Here are some common mistakes to watch out for when solving this problem. First, many solutions fail to handle edge cases for arrays with fewer than 3 elements. Since the zigzag condition is automatically satisfied in such cases, the output should be 0. Missing this can lead to runtime errors or incorrect results. Next, modifying the array in place without proper care can cause issues. For example, if you adjust nums I1 while iterating, it might affect comparisons with nums I+1 later. To avoid this, always use a copy or calculate adjustments separately. Another common mistake is overlooking the strict inequality requirements. The problem demands strictly greater or strictly less comparisons, so using equals or equals by mistake can result in wrong answers, especially when dealing with duplicate values. Lastly, a greedy approach that doesn't account for both zigzag patterns, odd indices high and even indices high, often leads to suboptimal solutions. Both patterns must be evaluated to ensure the minimum cost is found. Another mistake to be aware of is relying on inefficient brute force approaches. Generating all possible zigzag configurations, such as through permutations or exhaustive adjustments, results in exponential complexity. This becomes infeasible for larger arrays, especially when n can go up to 10,000. To solve this problem effectively, focus on minimizing the cost of adjustments for two separate patterns, one where odd indices are higher than their neighbors, and another where even indices are higher. By evaluating both patterns independently and returning the smaller cost, you can achieve the optimal solution. Instead of modifying the array directly, calculate the adjustment cost for each element to satisfy the zigzag condition. This avoids unnecessary computations and also preserves the original data, which is especially important in interview scenarios. Recognizing that this is a variation of greedy optimization is key. Problems like this often appear in interviews, so mastering the approach here will prepare you for similar challenges. When discussing your solution, it's important to explain the trade-offs involved. For example, why a brute force or in-place solution might fail, and why a two-pass greedy approach is the most efficient option. Interviewers value clear analysis of these trade-offs. Additionally, there are related problems that can help deepen your understanding of this concept. LeetCode 376, Wiggle Subsequence, focuses on alternating patterns, but it deals with subsequences rather than modifying the array. LeetCode 280, Wiggle Sort, involves rearranging an array to achieve a zigzag pattern without changing individual values. LeetCode 135, Candy, is another greedy problem where adjustments are made under constraints, which is useful for practicing similar logic. Finally, LeetCode 1247, Minimum Swaps to Make Strings Equal, emphasizes minimizing changes to satisfy given constraints, helping you practice optimization techniques in a different context. Now let's compare alternative approaches and their trade-offs. The brute force approach involves generating all possible zigzag configurations by adjusting each element and calculating the total cost. While this guarantees correctness, it has an exponential time complexity of 2 to the power of n, making it impractical for large arrays. The optimal solution is the two-pass greedy approach. Here, you make two passes through the array, one assuming odd indices are high and the other assuming even indices are high. For each pass, calculate the total adjustment cost. This method is efficient, with n time complexity and 1 space usage. Another option is the dynamic programming approach, where you maintain a DP table to store the minimum adjustment cost for both zigzag patterns up to each index. While this approach is effective, it requires n space and is generally overkill compared to the greedy solution. The two-pass greedy method strikes the best balance between simplicity and efficiency, making it the recommended approach for this problem. Great job! To recap, we focused on transforming an array into a zigzag pattern while minimizing the number of decreases. We learned about efficient local comparisons and explored edge cases. Thanks for tuning in, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!